Hello, in this video we're going to review some basic notions regarding vector geometry, namely the dot product, the cross product, and the notion of a normal vector. This is just going to be a review, so I will not prove the formulas I'm going to write, but it's kind of nice to have them all gathered in one place. So let's begin with the dot product. So this is all happening in R3. So if I take two vectors in R3, so if A has coordinates A1, A2, and A3, and B has coordinates B1, B2, B3, then the dot product is just what you get when you multiply the corresponding coordinates and add them. So in particular, this is a scalar, this is a number. So a dot product takes two vectors and spits out a number. There is another way to look at this. Another way to write this formula. So this number is the same as the length of the vector A times the length of the vector B times the cosine of the angle between the vector A and vector B. Note that whether you measure the angle from A to B or from B to A, it doesn't matter because cosine is an even function. So cosine of a positive alpha is the same as cosine of negative alpha. So an example. So if I take two vectors, let's say one vector whose length will be 2, so that will be my vector A, and its length is 2. And another vector, B, let's make it a little longer, so that the length of the vector B is 3, and suppose that the angle here is 120 degrees, then the dot product is going to be the length of A times the length of B, now this is just times, not the dot product, times cosine of 120 degrees. But cosine of 120 degrees, that is the same as cosine of 60 degrees, but with a negative sign. So that's just minus 2 times 3 times negative 1/2. So this dot product gives you minus 3. One thing to notice that if the vectors form a right angle, if the angle between A and B is right, then the dot product is 0, because you get cosine of 90 degrees here, and cosine of 90 degrees is 0. Let's move on to the cross product. So the cross product is an operation that is actually only specific to R3. You can make sense of the dot product in Rn, in any n-dimensional vector space, but the cross product is only specific to the three-dimensional space. And what it does, it eats two vectors and it spits out the third vector. So how does this work? So if I take two vectors, A and B, and suppose they lie in a plane. So here's a plane, and on that plane we have vector A and vector B. There's some other vector B. And here is an angle between them. Then A cross B is a vector perpendicular to the plane in which A and B lie. So that means the answer, the A cross B, is going to lie on the line that's perpendicular to this plane. So the thing that I have to determine about this vector is how long it is and whether it's pointing down or up. So the length, whose length, so such that the length of it is equal to the length of A times the length of B times the absolute value of the sine of the angle between A and B. So that gives me how long it is, and its direction is determined by the right-hand rule. What does that mean? So, while the dot product is commutative, whether I do A dot B or B dot A, it doesn't matter. The cross product isn't. It matters which vector comes first. So if it's the vector A that comes first, that means I look at the angle and draw an arrow on it like this, from the first vector to the second vector. And then what do? Then I imagine, sort of, that this thing here this plane is really a lid to a jar. Okay? And this A to B tells me which direction I'm supposed to be turning this lid, this plane. So it tells me to go like this, so inside the board, so that's counterclockwise. So if I do this, so that means I'm rotating it this way. Yeah, like that. And the question is, if I do that with the lid, if I rotated it like this, will the lid go up or down? Well, it's quite, if you know how to unscrew jars, you know that if I rotate it like this, it's going to go up. So that tells you the direction of this vector. Note that if I was trying to compute the cross product of B with A, so B cross A, then the angle should go the other direction. So that means I'm supposed to be now rotating it like this. So if you rotate this lid like this, you see that it actually goes down. You screw it in. So then you get it the same length, but pointing in the other direction. So one property of cross product is that if you just change the order, you just get negative of that vector, so vector pointing in the opposite direction. One thing to notice here is that if the angle between A and B is 0, so if A is parallel to B, then the cross product is the 0 vector this time. I mean, how do I know that? Well, ignoring this part, because then there's no plane in which A and B lie, you can look at the length, and then you see if the angle, if the vectors are parallel, so that means they form the angle of 0 or 180, then sine is 0. So that means the length of this vector will be 0. So it must be the 0 vector. Okay, there is some relationship between the cross product and the dot product that we will actually use, and I encourage you to look up in some analytic geometry book a proof of it, but I'm not going to prove it here. But it's a useful relationship. Namely, if I take 4 vectors and I do the cross product between A and B, and then the cross product between C and D, this is a vector, right? And so is this. So I can take, it makes sense to take dot product between these 2 vectors. And it turns out that that is the same as, so this now, our whole thing is a number. It's a scalar. So that's the same thing as A dotted with C. So that is a number, times B dotted with D, that is also a number, minus A dotted with D, this is also a number, and then times B dotted with C. This is essentially the only relationship between cross product and dot product we're going to use in our calculation. So don't try to memorize it, but here it is. And finally, what are normal vectors? So the first thing I wanted to tell you is about unit vectors. So a unit vector is a vector whose length is 1. And I can actually cook up a unit vector out of any vector you give me. So if V is any non-zero vector, then if I do V divided by the length of V, which means, what does it mean to divide a vector? That means this is just a number times a vector. Then if you compute the length of it, this is actually, the length is actually 1. Then the length of that is, well, this is just a number, so I can take it out. And this is not a dot product, this is actually just times between 2 numbers, so that's 1. So V, this is a unit vector. And finally, what is a normal vector? So normal vectors are vectors to a plane, vectors that are perpendicular to a plane. So suppose I have a plane then drawing I can think of a vector, I can think of a line, let's say I have a point here, line that goes through this plane at some point. So a normal vector is a vector that's perpendicular to the plane. So it's perpendicular to any line that lies on the plane, and it has unit length. So a normal vector to a plane is a unit vector perpendicular to the plane, i.e. perpendicular to any line lying on the plane. Of course, how many normal vectors are there to a plane at a given point? 2, one pointing up and one pointing down. There is a nice way to get normal vectors to a plane, namely, suppose I take 2 vectors that lie on the plane, A, B. So let A, B be any 2 vectors non-parallel that lie on the plane. Then I already know that A cross B, the cross product, is a vector that's perpendicular to the plane. So it's going to lie, in this case, because we go like this, it's going to actually point up. So this vector is definitely perpendicular to the plane. Perpendicular to the plane. So is it a normal vector? Well, I don't know if it's a unit vector. I don't know what its length is. But if I take this and divide it by its length, now I know, from what we've been talking about just a moment ago, any non-zero vector divided by its length gives me a unit vector. Then this is a normal vector. To the plane. By switching the order of A and B, you get the normal vector in the other direction. Yes, just to maybe comment on this, I think I didn't comment on it when I was talking about the unit vectors. Dividing a vector by its length or multiplying by 1 over its length does not change its direction. It doesn't change where it actually points. It only scales the length of it. So when I take this is perpendicular to the plane. If I divide it by its length, I still get a vector that is perpendicular to the plane. The only difference is it now has a different length, namely it has length 1.